Welcome to The Explainer. Today we're diving into a really powerful story about data, disease, and discovery. It's a story about finding a tiny, life-saving signal that's hidden inside a massive mountain of genetic noise. So let's just jump right in. Imagine you're a scientist, and you're staring at this exact problem. You've got data on thousands of genes. How on earth do you figure out which handful are the ones that actually matter for disease? Well, we're going to follow a real-world case study to see exactly how they do it. So the specific puzzle we're looking at involves two types of blood cancer. One is called acute lymphoblastic leukemia, or ALL for short, and the other is acute myeloid leukemia, or AML. Now, they can look pretty similar, but on a genetic level, they're completely different beasts. The challenge? Find a rock-solid way to tell them apart using just their genetic data. To get started, the scientists went big. They didn't just look at a few genes. They started with this enormous data set, measuring the activity level for over 3,000 different genes. You can think of it like each gene has a volume knob, and they measured where that knob was set for every single patient. And all of this information came from a group of just 38 patients. 27 of them had ALL, and the other 11 had AML. So, it's a pretty small group of people, but a huge, huge amount of data for each person. The whole point of this exercise is to cut through all that complexity. The idea is that somewhere in those thousands of measurements, there's a distinct pattern, kind of like a genetic fingerprint or a signature, that's unique to each type of cancer. And finding that signature is everything. Okay, so how do you find this signature? Well, you call in a detective. And our first detective is a really clever statistical method called SAM. That stands for Significance Analysis of Microarrays. Its whole strategy is about figuring out the difference between a real pattern and just random chance. The big idea behind SAM is actually pretty brilliant. It basically asks, hey, what would my data look like if this was all just random luck? And to answer that, it takes the patient labels, ALL and AML, and it just randomly shuffles them up over and over again, creating thousands of what-if scenarios. So here's how it works. First, it scores every single gene based on how strongly it's linked to a cancer type in the real data. Then it does the exact same thing for all those thousands of randomly shuffled data sets. Finally, it compares the real score to that whole sea of random scores. The genes that really stand out from the random noise, those are your signals.
Now, this is super important. When you're testing thousands of things at once, you're bound to find some that look important just by pure dumb luck. That's where a concept called the false discovery rate comes in. You can think of it as your fool's gold detector. It estimates how many of your so-called discoveries are probably just noise. You want to keep that number really, really low.
So the scientists have to make a very deliberate choice here. They look at this table to pick a cutoff, which they call delta. And they decide to be pretty conservative, picking a delta of 1.11. Why? Because this choice means that even in a worst-case scenario, their fool's gold rate is only going to be about 5%. They're setting a really high bar for what gets called a discovery. Okay, so after running the whole analysis with that strict cutoff and adding one more little filter for good measure, SAM comes back with its list of suspects. It has pinpointed 131 genes that it thinks are at the very heart of this cancer's genetic signature. But, good science is all about checking your work. You never rely on just one source. So to really be sure, the researchers brought in a second detective, a completely different statistical tool called LIMMA, which has a totally different way of hunting for the signal. And here's where it gets really cool, because these two detectives have totally different philosophies. SAM kind of treats each gene like its own little island, but LIMMA's a team player. To make a decision about any one gene, it actually looks at the patterns across all 3,051 genes to get a much better, more stable picture. It literally borrows strength from the whole data set. This whole borrowing strength thing has a fancy name, a moderated t-test. But what you really need to know is that it makes the analysis way more powerful and reliable. And that's a huge deal, especially when you have a small number of patients like we do in this study. So LIMMA runs its own analysis using the same strict quality filters. And what does it come back with? Its own list of significant genes. The number? 129. All right, here it is, the moment of truth. We've sent in two different detectives using two very different methods to look at the same evidence. They've both come back with a list of suspects. The big question is, did they point to the same culprits? And the result is just stunning. Of the 131 genes SAM found and the 129 that LIMMA found, an incredible 129 of them showed up on both lists. They were identical. So what about the disagreement? It was tiny. Only 2 genes were flagged by SAM that weren't also flagged by LIMMA. That's it, just 2. I mean, come on, that is the scientific equivalent of a slam dunk. You have 2 independent, totally different approaches looking at this massive, noisy data set, and they come to virtually the exact same conclusion. That gives you incredible confidence that the signal they found is the real deal. So, with that confidence, there's one last step. We need to actually visualize this genetic signature and see if it works. Can this list of 129 genes actually separate the 2 groups of patients? Let's turn the data into a picture. To do that, they create what's called a heat map. It's a fantastic way to see everything all at once. It's super simple. Each column is one of our 38 patients. Each row is one of our 129 key genes. And the color tells the story. Bright red means that gene's volume knob is turned way up, while bright blue means it's turned way down. And just look at that. That is the payoff right there. The analysis totally worked. You can see 2 completely distinct clusters. The computer, using only the patterns from these 129 genes, has automatically sorted the patients into 2 groups, almost perfectly separating ALL from AML without anyone telling it who was who. In fact, it was nearly flawless. As the original researchers put it, every single AML patient was grouped correctly, and all but one of the 27 ALL patients were grouped correctly. Think about what just happened. We went from a noisy sea of over 3,000 genes down to a crystal-clear, actionable signal. And this really makes you think, doesn't it? This whole story is a profound reminder that the answers to some of medicine's biggest questions might not be in a new test tube, but might already be right there, hidden in the data, just waiting for the right statistical detective to come along and find the signal in the noise.